All right, so dimers. We've seen already a few times this week, but I'm going to start with a reminder in the general setup when we deal with planar bipartite graphs. So here is a planar bipartite graph, and we're looking for dimer configurations, something like this. Hopefully I can manage it. Okay. And in general, we have a weight function on edges. So there is some positive real number assigned to each edge, and we define the weight of a dimer configuration as a product of the corresponding edges, of the weights on edges which are in this dimer configuration. And then the probability of a dimer configuration is proportional to the weight of the dimer configuration. So this is 1 over z, where the normalizing constant or the partition function is simply the sum over all possible dimer configuration of the corresponding weights. Okay, so we saw a weighted version at least for the square lattice and the Aztec diamond, but this is how to define it in general. And we can define the Kasteleyn weights. So let us define first of all, what is the Kasteleyn sign condition? So since we deal with bipartite graphs, all faces are of even degrees. So for each simple face of degree 2k, there is a choice of signs, complex signs in this setup. I'm going to deal with tau I are complex numbers with absolute value equal to 1. And what we want that the alternating product around each face is plus or minus 1, depending on the degree of the face. So if those weights are tau 1, tau 2, etc., tau 2k, then tau 1 divided by tau 2 times tau 3 divided by tau 4, etc., tau 2k minus 1 divided by tau 2k is equal to minus 1 to the power k plus 1. So the product of all red edges divided by the product of yellow edges is minus 1 to the k plus 1, where k plus 1 is related to the degree of the simple face. And then one can define a Kasteleyn matrix which is the following. So for each two adjacent white and black vertex, the weight is the corresponding weight on this edge times the Kasteleyn sign of this edge. So this is if W and B are adjacent, and it is 0 otherwise. Recall that we deal with the quarter of the adjacency matrix. So rows are indexed by white vertices and column by black vertices. Then what is known that as soon as you can choose you always can choose, as soon as you have chosen already Kasteleyn sign which satisfies this condition, there is a Kasteleyn-Perkus theorem that the partition function in this setup is given by the determinant of the Kasteleyn matrix, and we've seen already that also all local statistics can be computed in terms of the inverse matrix. All right, so this is a reminder for the general setup for planar bipartite dimer model. And now I'm going to introduce an object which is called a T-graph. And then I will explain how it is related to dimers and what else we know about it. And this is due to Kenyon and Sheffield. All right. So assume that we start with any convex polygon, let's say rectangle. And we're looking for a tilings of this rectangle by the open edges. So let me first draw a picture, then I will explain more what I'm talking about. Something like that. So consider the set of open edges. So Li is an open edge with endpoints on either Lj or P, where P is my polygon which I start with. So also we ask that those edges do not intersect. And let us call endpoints which lives on the boundary, which lives on our polygon, root vertices. And then the last condition is that if we consider the union of those open edges from I equal 1 to n together with the root vertices, then this is a closed set. Okay. So why does it call a T-graph? Because the typical vertex of a T-graph is look like T, right? So here it is. You have an endpoint of the open edge on the other edge, and the typical thing is a T letter. We can consider it as a graph, right? We have vertices which are endpoints of those edges. So there is a very natural graph drawn on the picture by this tiling of the polygon. Yeah, also let me call those edges Li. We're going to call them complete edges. I will need it later to have different notions for a piece of the edge or for the whole edge. So we call those segments complete edges. All right. Now that this set of edges will tile the polygon by convex faces, right? So I have a set of convex faces, And I claim that, okay, let me call it lemma, that the number of faces is equal to the number of complete edges plus 1. So there is one more face than the number of edges. And this is obvious from Euler's formula. So proof follows from okay. Now note that we can define a very natural random walk on those graphs by saying that, okay, from each vertex, there are two possibilities to go to the right or to the left with probabilities which are proportional to the inverse of the corresponding edges. So there is a if this is vertex V, then it has two possibilities to go to the right, to the left, with probabilities proportional to the inverse of the Euclidean length of the corresponding edge. Okay. So let me draw all vertices of the T graph. And we call this graph GT. And note that this edge never participates in the random walk, because there is no way to go through this edge. From this vertex, we always go to the right or to the left. So this one just never participates in it. And just a comment, and okay, I'm just putting different arrows. So from this one, we can go to the right, to the left, here right, left, and here right to left as well. Oh yeah, this edge also never participates in the random walk. All right. So let me make a comment. Today we're going to deal only with non-generate setup, but okay, as soon as you have vertices which look like this of the T graph, then this is a non-degenerate setup. However, in general, you might have something which looks like this. This is degenerate. However, it never happened like this. So this is just not allowed. So what is the problem with this vertex? There is a half plane with no edges at all. So this is forbidden. You never have this. But you don't need to think about these two cases today. Today we're going to deal only with non-degenerate T graphs. So all vertices looks like T. All right. So now how this is related to the Dymers model. And first, let us define a Dymers graph starting from a T graph. So okay. Let me try to repeat this picture again. All right. And we say that faces correspond to white vertices of the dimer graph. And each complete edge corresponds to a black vertex of the dimer graph. So the whole complete edge, this is just one black vertex. However, remember this, and we want our bipartite graph to be balanced. So we need to get rid of one of white vertices. We can just choose one on the boundary and say that this is not a part of our bipartite graph. So we want to define the graph GD, which is the dimer graph. So this is a union on white and black vertices, where white vertices are faces of GT without one boundary face. Black ones are just complete edges. And we say that two vertices are adjacent, so white and black vertex are adjacent, if part of the corresponding complete edge is the side of the corresponding face. So let me draw the graph. So this one has two edges. It's connected to this one and to that one. Okay, this one is connected to this one and also to this one. I will explain in a second why I'm drawing edges in such a way. So this one has three adjacent black vertices. This one have 1, 2, 3, 4. And this one have 3 ones. Okay, now it should be well visible. And the way I draw edges, this is to emphasize that the vertices of the dual graph correspond to the inner vertices of the T-graph. Right, so each vertex of the T-graph corresponds to the face of the bipartite graph. All right, so let me maybe draw on the side what is this bipartite. This is this one. We get just this bipartite graph starting from a T-graph. And okay, for example, this white vertex and this black vertex are, which ones? This and that, I guess. Okay. So now we have a bipartite graph given the T-graph, but also we can define weights on edges using the geometrical picture of a T-graph. So let us define the Kasteleyn matrix. As following. So for each two adjacent vertices W and B, we define the Kasteleyn matrix entry as following. So I say that the edge weight on WB is given by black one. So let me name these two vertices as V prime and V, and I say that this is the length of V prime minus V, and the Kasteleyn weight itself is V prime minus V without the modulus. So what I'm doing, I'm looking at this white face, I'm looking at the corresponding adjacent black edge, and we look at the piece of the edge which is the side of the corresponding white face, okay? And we say that the corresponding complex vein is just correspond to this vector, so this complex number, and okay, I need to decide which direction to orient this edge. I will say that the white vertex is always on the left of my edge, okay? So now we have, is it clear how we define the Kasteleyn weights?
So the point is that it's not the whole length of the complete edge,
yes,
but just a portion.
Yes, it's just a portion, and which portion? This is exactly the portion for this, which is the side of the corresponding face. Okay. Okay. So, for example, on this picture, if we take our K and W, then this is a KWB. Okay, like there is no problem to say that this is a way to define edge weights. However, I need to explain why this is Kasteleyn weights. So I need to check the Kasteleyn sign condition, right? Because remember, we need this alternating product to be plus or minus 1 depending on the degree of the phase. And to claim that this is my Kasteleyn weights, I need to check the Kasteleyn sign condition for those weights, that this geometry agrees with the Kasteleyn sign condition. Okay, so to do this, let us check the to do this, yet again, recall that what are faces of the dimer graph? The faces of the dimer graph correspond to the vertices of the T graph, right? And the Kasteleyn sign condition is around each face, so we need to check that it holds around each vertex of the T graph. Right, so this is the face of the dimer graph, which correspond to the vertex of the T graph. And what are the Kasteleyn signs? So those are directions of these edges. For example, if this is tau 1, tau 2, then what is tau 1? We agreed that it is on the left. So the unit vector in the direction of this edge going towards the vertex of the T graph is tau 1, right? And this one, this is tau 2. Okay, right, because we choose this direction and we agree that the white face is always on the left of the edge. So, and this is the same for the, okay, tau 3. Tau 4, here again, tau 3 is this one, and tau 4 is that one. So what is the ratio of these two guys is -1. And this is true for all those edges, except the last one. Because for the last one, what we have, so this one goes this direction, and this one goes to the same direction. So those two directions are the same, which gives me that tau 1 divided by tau 2 times etc. times tau 2k minus 1 divided by tau 2k is equal to -1 to the power k minus 1 times 1. Where k minus 1, this is all but one black vertices of this phase, right? There are k minus 1 of them, and the last one gives 1. So we have this one. Okay, this is indeed -1 to the k plus 1, which I use as a definition of the Kasteleyn sign. Okay? So T-graph give us bipartite graph together with weights, which are geometric lengths of the corresponding sides of the polygons, and Kasteleyn signs as well, where Kasteleyn signs are complex Kasteleyn signs and given by the directions of the corresponding edges. And we just check that indeed they satisfy the Kasteleyn condition. Okay? Okay. Good. And now let us forget for a second about dimer graph and think about spanning trees. On the dual of the T-graph. So first of all, how do we define the dual of a T-graph? And here I will draw a little bit bigger picture to have more faces and edges. Okay, yeah, let us look at something like this. And what is the dual graph of a T-graph? So, okay, faces of a T-graph are vertices of the dual graph. And we say that they're adjacent if they are adjacent to the same piece of the complete edge. I guess I draw all edges of the dual graph. And now we're interested in spanning forest on the dual graph, on this graph. So first of all, what is a spanning tree, sorry. So definition, just a reminder that a spanning tree is a subset of edges which form, first of all, the connected graph. There are no loops. And all vertices are covered. And there is a notion of the directed spanning tree if we deal with directed graphs, so where edges have a direction. So I will just add here in color that a directed spanning tree, how do you call it? I forgot. Which is also called an arborescence in computer science. So a directed spanning tree, we just need to add that every vertex, every vertex, but one, which is a root, has exactly exactly one outgoing edge. And then we also can define a spanning forest. So this is again the subset of edges such that there are no loops. All vertices are covered. And each component connected to a unique root vertex. In other words, it's just a union of trees which cover our graph. And again, it is directed or arborescence if every non-root vertex this is not visible, right, for half of the people. Sorry, I forgot about. We can fix it. So if every non-root vertex has a unique outgoing edge. Okay, so let us just draw an example of the tree on the dual graph. Something like that. I hope that yellow is distinguished from white. You can see it. So this is a tree on the dual graph. And know that vertices and dual vertices, edges and dual edges are in bijection. Clearly, this is how we define the dual graph. And I claim that the complement of each tree on GT star, is the forest on the initial T graph. So here is a proposition. So a complement similar, the complex on the forest on the initial T graph is the tree on the dual graph. Spanning tree. Everywhere add spanning. Okay, so let us first of all see it on this example. So we just need to take a complement. So this edge is not taken, this edge is not taken. This one over T graph. What else? This one. This one. And this one. At least on the picture, it is indeed a forest, the dual, the complement of the, with roots on the boundary. So here there is nothing. Oh, this one as well. Now how to prove it? There is a classical duality argument. So note that if we started with the tree on the dual graph, then the complement of this tree cannot have loops, right? Because if there is a loop, this loop will surround a piece of the graph. We know that it is connected, so there is no loop. It cannot happen because edges and the complement of those edges cannot intersect. So therefore, the remaining graph at least doesn't have any loops. So we just need to check that this is a spanning forest, meaning that it covers all vertices of this graph. I'm not going to do it in a proper way. I will just give you an idea of how to do it. So similarly, the opposite direction, if you have a spanning forest, okay, so sorry. We also need to check that the two vertices, root vertices, are not connected by the complement. Again, it cannot happen because if they are connected, then some part of the graph is separated for the rest of the graph, which cannot happen because we have a connected tree which covers all vertices. And the opposite direction is the same. Start with the forest and say that, okay, the complement is connected. It doesn't have any loops. Idea is exactly the same. If it does, then it will surround some vertices of the T graph, which cannot happen. Okay? Just use the duality of the picture. So, and you will get the proof of this proposition. All right. Okay. Now, this proposition is about non-directed trees and non-directed forests. What about directed ones? And moreover, let us use a direction which is from direction on edges, from what we started, right, from this Markov chain. So we have a clear direction. For example, there is this edge which never participate, or this edge is oriented in both directions, but this one is oriented only to that side. Okay. I'm going to show that there is a connection of marked dimer configurations with directed spanning forests. But first, I need to define the marked dimer configuration. So back to dimers. And what is the difference? We defined already dimer configuration with some weights given the T graph. But now I want to define the marked version. So what is the difference? So, OK. To define the marked configuration, first of all, you need to choose a dimer configuration. And then so I'm going to explain what does it mean. So recall that here, what was the weight? The weight was the piece of the complete edge which correspond to the whole side. However, some of those pieces are divided by vertices of the T graph to smaller pieces. And instead of taking the whole side of the face, we're going to choose one of the single pieces. So we have all these pieces which are a part of this side, and choose one of them, just part of it. Okay? So let me draw a picture. So this vertex is not participating in our dimer graph. I have only those white vertices. And then I have black vertices. And I'm not going to draw a bipartite graph. Instead, I will just draw the dimer configuration, one of the dimer configuration of this graph. For example, this one. Okay. Right, so we're done with A. We have a dimer configuration. Now we need for each side of the corresponding face to choose one of the single pieces of this complete edge. So let us do it. Okay. No, sorry, this is not what I wanted. I wanted this one. Just to follow example which I have. Okay. So for this edge, there is no choice, right? This piece is a single piece, which is a part of this side. So I need to choose this as a part of this procedure. For this one, again, there is no choice. So I take the whole edge. Now, when we go here, what is the side of this face? This is whole. This is whole this edge. And what I need to do, I need to use just one of those pieces, right? There is a vertex of the T-graph in the middle. So I'm allowed to choose either this part or that one. Okay, so let me choose this one. Now for this edge, again, there is no choice because this is the whole single piece, which is the side of the face. Let's go here. Here again we have a choice. There are two pieces, either this one or that one. I'm allowed to choose, and I have to choose only one of them. Okay, for example, this one. Then here, again, we need to choose one of these two pieces. I choose this one. And here there is no choice. Okay? So the difference with the previous construction is that instead of the whole side, we choose just one single piece of the corresponding side of the corresponding face. And you choose them with probabilities proportional to the length of those pieces. So now my new probability measure on marked dimer configurations, so the probability of each dimer configuration is a product of those pieces. Where by prime, I mean that we choose one of the pieces of the corresponding side of the edge. Okay?
So can you re-explain what's the condition on the kind of pieces you can choose? Sorry.
So we have a white face, right? And I'm thinking about the weight here. I have chosen this edge as a part of the dimer configuration, but this piece can be divided by lots of pieces, right? So I have my vertices of the T-graph, which divide this side of this edge by 1, 2, 3, 4 pieces in this setup. And I can choose only one of those 4 pieces instead of the whole one. So I choose either this or that or that or that. I mean, I can choose this one, for example.
So it cannot be the whole one. It has to be one of those.
It has to be one of single pieces. Yes, it cannot be the union of few pieces this time. Right? It has to be a single edge of a T-graph. Because if I take this one, this is the 2 edges of a T-graph. This is this edge and this edge.
So okay.
This might be stupid, but does it all depend on where you place the black vertices on the open edges?
No, I just was making choice such that it's a nice picture. No, I mean, here is an example, right? I can choose this one.
Okay. No, but in the beginning, you choose where you put the black vertices along the edges.
Oh no, for example, this black edge can be shown like here, right?
Yeah.
But I'm not allowed to choose this piece for this edge. Okay? Yeah.
When you multiply S prime E is the length.
Yes. Yeah. Okay. So we first choose a dimer configuration, and then we choose pieces which give us the measure on this marked dimer configuration. Okay? All right. So, and what is the connection with the directed forest? Now there is a bijection between marked dimer configurations and directed spanning forest on a T graph. So, okay. Let us prove it. And to prove this, we're going to use the temporary bijection of those dimer configurations with trees on dual graph. So how we construct a tree starting from this marked configuration. So we have these white faces. And we have a dimer configuration with a choice of marked piece of the T graph, which is a single edge of a T graph, right? So what I'm doing, I'm going to draw the directed edges between white vertices in the following way. We take the white vertex, we look at the corresponding black vertex, which is in bijection, which is in dimer configuration, sorry, and we draw an edge to the white vertex oriented in this way. And how we choose this white vertex, this is the one which is adjacent to this one through this edge, okay? So from this picture, we obtain the following graph, directed graph. So this one connected through this one, I draw this. This one, I choose this piece. So we go here, and direction is given by this. Here, we go here, go there. Note that by this construction, each vertex has exactly one outgoing edge, right? Because this is how I draw those directions. I choose the one which corresponds to the dimer, and this is the only one which is outgoing edge from this vertex. It is, now we need to check that it did give us a tree, that there are no loops. And I claim that this is true, but what happened if we got a loop? Imagine for a second that, for example, here, I have another directed edge which form a loop. Let us think what is inside this loop. Inside this loop is a T graph. What do we know about the T graph? The number of faces is one more than the number of complete edges, which means that what is inside this loop cannot be covered by dimers, right? There is one more white vertex than black one. So it never can happen because of Euler's formula, which means that there are no loops. And note that starting from each vertex, we always keep going unless we went outside of the graph. So there is a path from each vertex to the root vertex. Yes?
How do you choose direction?
Yet again, we look at white vertex. We look at the corresponding dimer configuration. which give us a piece of the corresponding, an edge of the T-graph. And we connect this vertex with the adjacent white face with the direction this is an outgoing edge.
We had to pick the first one to start with.
It doesn't matter, you can start from any of them. I start from this one. This is my edge, so which means that the direction is this one. I'm drawing a directed edge which corresponds to a dimer starting from a white vertex which contains in this dimer configuration, right? And now it is adjacent with a white vertex which is not connected to this black in a dimer configuration.
It's not enough to look just at the orange pieces of edges. You really need the underlying dimer configuration.
Yes. Yeah. Yeah, thank you. This is exactly what gives me this direction. Okay. All right, so we have a tree on the dual graph constructed from a dimer configuration. We already know that the complement of the tree is the forest on the T graph, right? So we know that it is a forest. What we need to check that it is a directed forest. Remember that we have directions which are fixed by our Markov chain. So I know for sure that the complement is a forest. I just need to check that this is a directed one. Okay. But now note that what happened with each complete edge. So since it corresponds to a black vertex, there is exactly one piece which is chosen on this complete edge, right? Which is a part of our marking. So for example, this one. Then I can orient all edges on this complete edge going away from this marked piece. So I just choose everything here, go that direction, and everything there go this direction. So note that this is the direction which we do have in our directed graph, right? Okay, so I claim that if we choose this direction at each edge of the complement of the marking, then it gives us an oriented forest, directed forest. But okay, like note that given this choice of directions, each vertex of a T-graph has exactly one outgoing edge, because it might have outgoing edges only on this complete edge. And I choose a direction for all those vertices. Everything which is on the right goes that direction, everything on the left goes this direction. And as soon as we get here, note that at this complete edge, there is exactly one marked piece. It might be somewhere here, which means that there's also direction chosen already, so all of those ones going this direction. So we can always keep going as soon as we started from any vertex, and we finish only when we reach the root vertex. So we know that it is a forest, and I just defined the direction, and now we know that this is a directed forest. Okay? All right. Okay, so the opposite direction is similar. Again, I can start from the forest and inverse everything what I said to get the marking for this dimer configuration. All right. I have this probability measure on marked dimer configuration. I also can define the probability measure on the directed forest. And let us define it in the following way. So this is the product of 1 over SE prime over edges in the forest. So recall that here transition probabilities were proportional to inverses of the Euclidean length. So let me define it. Okay, I need to normalize it by constant, so it is proportional to this one. But what is this? This is the product of SE prime, which correspond in the marked configuration, divided by the product of all edges of the T-graph. So the probability of the marked configuration is the same as the probability of the corresponding forest, directed forest on the T-graph. All right? Okay. By the way, this temporary bijection, which I hopefully explained, this is where the SLE appear in dimer models. So like these branches of the uniform spanning tree converge to the SLE2, and this is a hidden way how you get SLE in the dimer model. This is what Evelina mentioned yesterday. Also, I should say that this bijection between trees and dimers is crucial for the sequence of work, which is called imaginary geometry, and we have one of the experts in the room, Nathaniel. If you want to learn more about it, ask him. All right, let me keep going. Good. So now we know this bijection, and we know how to get the dimer graph starting from such a drawing. Now the question is, could I start with planar bipartite graph and some arbitrary weights on this planar bipartite graph on edges? Is there a way to draw the T graph starting from such a graph? So, and the answer is yes, and let us do this. Okay, I don't need this anymore. So, all right. So assume we started with, I'm going to draw a small example, finite graph. Something like this. I have some edges, generic weights on edges. Is there a way to embed this graph as a T-graph, right? Where all white vertices correspond to faces of a T-graph and black vertices correspond to the complete edges of a T-graph. And we're going to do the following. So before I start, I need to define the dual graph. So all inner faces are indeed vertices of the dual graph. On the boundary, I need to deal with it a little bit. So let me do the following. Let us use one black vertex and call it B0 on the boundary, and others are W1, W2, etc., Wm. So we have the outer face of degree 2m. And let me add edges to the infinity, which are connected with all white boundary edge vertices. and this one black one. Okay? And now I have a dual graph which has 4 outer vertices instead of 1, if we start with the initial one, and I want to embed it as a T-graph. And we're going to embed it to the convex polygon, generic convex polygon with m+1 sides. Q0, this is going to be QM. So Q is a convex polygon, generic convex polygon with sides which are given by complex numbers Q1, Q2, Qm, etc., Q0. And the side Q0 will correspond to the vertex B0, and all other ones will correspond to the corresponding white vertices W1, Wn. Okay. How are we going to do this? So know that, yeah, here clearly Q0 is the sum minus sum of Qi. I'll need it later. I need some assumptions on graph. So assume that the initial bipartite graph at least has at least one perfect matching, has a dimer configuration. We'll also assume that there is no unused edges in this dimer configuration, which means that every edge contains in at least one dimer configuration. So no unused edges. And I also ask that each entry and 2 by 2 minor of the inverse Kasteleyn matrix is non-zero. Which, for those who knows, it implies that if for generic choice of weights this is always true, then the graph doesn't have no one cuts. One cut is a subset of a graph which has, okay, one correspond to the one more black vertex and white vertex, and all edges with a complement starts from black vertices of this subgraph. So, okay, anyway. So this is just like some generic assumption. So we have a nice generic graph with generic weights. This is how to think about it. All right. And let us deal with plus minus Kasteleyn signs. So the Kasteleyn matrix is real valued. So we have GD, which is a bipartite, planar bipartite graph, and the Kasteleyn matrix, which is real valued. Okay. Then I claim that there exists G, which can be defined on the set of white vertices, such that you can just solve this system of linear equations. We have that it has at least one configuration, so there is an inverse matrix which allows me to solve this equation. And I take this G, and about G now I can think as a function defined on the white vertices. So what's written here, how to think about it, we have our Kasteleyn matrix. Right, and now what I do, so columns correspond to white vertices, and I multiply, I forgot to talk about gauge equivalence. I multiply this whole column by G1, G2, etc., Gn. And what I know that the sum at each by first row is equal to 0.
The first entry of your vector here corresponds to which vertex of?
Right, so those are W1, W2, etc. First M1s correspond to the boundary white vertices. This one corresponds to B0, all other correspond to black vertices. I don't care what is the ordering there. Okay, so yeah, we have a matrix which is B0, then all other Bs, and here W1, Wm, and all other Ws. So now I define a new matrix, which is given by Kij times Gj, right? I just took this new matrix, which we get. Yeah, okay. Hold on. We need to go back to the dimer model.
So this G is just a column of the inverse Kasteleyn.
Yes. What? No, it's not a column of, it's a gauge function. I forgot to say what is the gauge for the dimer model, but I'm going to do it right now. So.
You sure you don't want GJ rather than GI in K tilde?
This is GJ.
Oh,
this is
okay.
J, sorry. Okay, this is my bad handwriting. Anyway. yeah, this is GJ. Yeah. Oh, and those are exactly these new entries which I get here. I think about my new matrix right now. I'll finish this process and then talk about gauge equivalence. Sorry. So now the next step is to say that there exists f such that fk tilde is given by q1, qm, 0, 0, right? This is another system of linear equations. So what do? Now we multiply each row by different f's. So this is f1, f2. This is not 1 anymore. This is with 1, 1. All others stay zeros, fn. And the condition which is written there is that now if we sum through columns, then we get q1, here we get q2, etc., qm, and then the rows of zeros.
So we pretend that we know the QIs?
Sorry?
Pretend that we know the QIs. At the moment,
They are given. We choose them. We start with a generic polygon. Yeah. And again, like these m's, those correspond, first m columns correspond to first two boundary white vertices. And they're exactly enumerated as it's shown on the picture. So this is W1, W2, etc. This one corresponds to W1, this corresponds to W2, etc.
so for every choice of polygon, there will be one such T-graph.
Yeah, for the generic choice of polygon. I want edges not to be like parallel to each other and convex polygon, yeah. Okay, so now important thing which I forgot to say. Which would explain why we were doing this. So let us look at weights around white 1 vertex. We have some weights U1, U2, U3, etc. What if we multiply all of them by the same constant? Just multiply by the same constant. Note that each dimer configuration contains exactly one of those edges, right? Because we need to cover this vertex and to cover it exactly once. Which means that if I multiply around one white vertex all weights by this constant, sorry, then this multiplied by this constant, this as well multiplied by this constant, so it doesn't change the dimer measure. So we say that two gauge functions are gauge equivalent if one can be obtained by another as a sequence of such multiplications, which is the same as, okay, we can define a function at each vertex. At white vertex, I will call it the function g. At each black vertex, function f, and say that this is a relation between those two guys. So note that this is exactly what we were doing here. So we were looking for a gauge, right? And I call this f and g a gauge function, pair of functions, which is a gauge, which defines exactly the same probability measure. So it doesn't change the probability measure. And what we were doing here in first two steps, I first choose this g, and then I choose this f as a solution of the linear system of equations, right? So now I can use these weights. Those are still Kasteleyn weights, because when we do this gauge, it doesn't change the measure. It still satisfies the Kasteleyn sign condition. So I have new Kasteleyn weights on edges, which gives exactly the same measure. And I claim that this one should give me the T-graph. So I absolutely don't have time to talk about this, unfortunately, I'm sorry. But let me at least tell you that with the boundary, we're done, right? What is B0? The sum of those guys, I now say that, remember what was the definition of, do I still have it? No, I don't. Okay. The definition of the Kasteleyn signs on the T-graph, right? So they're exactly written here. And we know that the sum along this row is equal to Q0. This is equal to Q0 because the sum over all elements is equal the same, right? Those are equal to Qm. Those also have to be equal to the sum. What I'm talking about? Yes. And I don't have time to explain it. I'm going to stop right here. We will continue on Monday.